In the lecture yesterday, we had a look at the various symmetries and belonging conservation laws. So let me just summarize briefly what we arrived at here. So the first symmetry we had a look at was translational symmetry. Along some direction which was characterized by a unit vector n. And we saw that the conserved quantity in the system that has such a symmetry is the momentum in the direction of this translational symmetry. So the component of the total momentum p in the direction where we have this translational symmetry will be conserved. The next symmetry we had a look at was rotational symmetry, in which case you had some axis around which the system would be invariant under rotations. And in this case, we found that the angular momentum, or more specifically the component of the angular momentum along this rotation axis, would be conserved. So we also commented that in a spherically symmetrical system, the total angular momentum would be conserved because the system is invariant in all directions. Now, there's one more very important example. In which case the energy is conserved. So the question is, what is the belonging symmetry that the system has to have in order for energy to be conserved? And that's what we'll start with today. The conservation of energy is probably one of the most used conservation laws in physics. You're all most likely very accustomed to using it when calculating various quantities, for instance, by using that kinetic energy plus potential energy is constant throughout some reaction. But there has to be some underlying assumption behind this. When can we actually state with certainty that the energy is conserved? And the purpose of this is to try to formalize the argument for when we can say that energy is conserved. So we'll start out with making the following assumptions about the system. We assume that we have a conservative system. Potential depends only on the position. And the Lagrangian can be a function of the generalized coordinate, its time derivative, and possibly time. Consider now the time derivative of L. So here I'm just using the product rule for derivation. I can write this as by using Lagrange's equation for the first term here. So this one is equal to this one. And by doing so, I am able to combine the first two terms into one term, which is the total time derivative of a new term. Like this. And if I now simply move this term over to this side, I get the following equation. So what we did here was to consider the time derivative of L and then use Lagrange's equation to obtain the following form. Now, I'm introducing an energy function, which is known as H. And I define it as follows. And this might seem a bit arbitrary at this point, but we'll see in a little while why this is called the energy function. So with this definition, we obtain this by combining these two equations. So far, the derivation is pretty general. The only assumptions we made was to have a position-dependent potential and a quite general Lagrangian, which could depend on the generalized coordinates, their time derivatives, and possibly time. What we're interested in seeing now is what happens if we assume that Lagrangian is actually time independent. So we assume that there's no time dependence in Lagrangian. Its partial derivative with respect to time is 0. And if that is the case, then this quantity has to be 0 based on this relation. In order to proceed, we're going to make use of something which is known as Euler's theorem. The following relation holds true if f is a homogeneous function of the nth degree. And what do I mean by this? Well, let's just take a trivial example. Let's assume that f is x raised to the power of 3. So it's a homogeneous function of the third degree. Let's see if Euler's theorem holds. So we should have x multiplied with the time with the derivative of f should be equal to 3 times f. And that's okay. Now, when we're dealing with the Lagrangian of the system here, we actually have a homogeneous function, which we can use this theorem on. And that is the kinetic energy. So, because we have that the kinetic energy is essentially 1/2 mass velocity squared. So let's then use Euler's theorem on the kinetic energy. And keep in mind that the kinetic energy is second order in the velocities or the time derivatives of the generalized coordinates. So the q's play the role of x in this example. So this is the left-hand side. So we should get this just by differentiating t. And this is equal to 2 kinetic energies. Sorry, should be a dot here. precisely because the factor 1/2 is missing here. All right, let's now use this result in our equation over here. And keep in mind that the Lagrangian is independent, the potential energy in the Lagrangian is independent on q dot, since we assume that it's only dependent on position. So we can replace L here with T, and therefore make use of this relation. So then that the energy function h should be equal to 2t minus L. And inserting for L, t minus v, we obtain the sum of the kinetic and the potential energy. So this gives you an idea why h is known as the energy function, because it's the total energy. So in other words, we have now identified the precise mathematical condition which gives us a conserved energy. The total energy of the system will be conserved if there is no explicit time dependence in the Lagrangian. In effect, its partial derivative with respect to t is 0. So we can now fill out the last block here, and I'm putting explicit in parentheses to emphasize that there should be no explicit time dependence in the Lagrangian. And in that case, the energy will be conserved. So the following table summarizes probably the most important symmetries and belonging conservation laws, and it's very important. Right. We're now going to move on to something which is known as Hamilton's equations. So far we've been discussing Lagrange's equations, and we did introduce Hamilton's principle. So we're now going to see how is this related to Hamilton's equations. And in fact, this H is known as the Hamiltonian of the system. So let me say a few words about the Lagrangian formalism compared to the Hamiltonian formalism, just as a precursory, so you can get an idea of how they compare. the first point is that Lagrange's equations are equivalent with Hamilton's equations. So the physics remains unchanged. What changes is just the method we use to analyze the system. Then one could ask, okay, if the two methods are equivalent, is one of them better than the other? Hamilton's formalism is not necessarily better or more suited than the Lagrange formalism in terms of obtaining a direct analytical solution for mechanical problems. So in this sense, it's up to your personal preference if you want to choose the Lagrange or the Hamilton formalism when analyzing some mechanical problem. However, there are a few areas of physics where the Hamilton formalism is actually more suited for analyzing the physics. And two such areas include quantum mechanics and statistical physics, in which case the Hamilton formalism is actually more convenient to use. So we're going to have a look at what this Hamilton formalism entails, what the content of it is. And to begin with, we'll just make a few quite general assumptions about the systems we'll consider. And it's basically the same assumptions we've been using mainly so far. Namely, we assume that the system is holonomic, which says something about how the constraints look in the system. And we also assume that the forces in the system will be monogenic. And this is a common term for forces that may be derived from two particular types of potential. Namely, our standard potential, which only depends on position, and a velocity-dependent potential, which we introduced in relation to the particle in an electromagnetic field. In which case, a generalized force would have to be written in this way for the Lagrange equations to remain the same. IE here means in effect. In order to compare the Lagrangian and the Hamiltonian formalism, we'll actually build a bridge between them right away. We'll see how you can start with the Lagrange formalism and then actually transform your equations to Hamilton's formalism. The tool we will use in order to establish this bridge between the two formalisms is known as a legendre transformation. So we'll have a look at this legendre transformation and the resulting Hamilton's equations of motion. So we'll start off just by briefly reminding ourselves of what the Lagrange formalism contains. We have n generalized coordinates. These are the n Lagrange equations. So we have n second-order differential equations. So in order to obtain a complete analytical solution for this system, we would need 2n initial conditions. And the state of a given system in this formalism will be specified by a point in the n-dimensional configuration space with axis spanned by qi, the generalized coordinates. So this configuration space is, for instance, the space that we imagined that the system could take a path through when moving from one point T1 to another point T2. So that's basically the Lagrange formalism in a nutshell. And we'll now see what the Hamilton formalism contains. Well, the first difference is that instead of having n second-order differential equations, we have 2n first-order differential equations. So we still need 2n initial conditions. The state of the system when using the Hamilton formalism will be determined by a point in a 2n dimensional phase space spanned by the axis qi and pi, where pi is a quantity we introduced in the previous lecture, namely the canonical momentum. Both q and p are known as canonical variables. So p is the canonical momentum, and q here is the canonical position variable or coordinate. Okay, let's have a look at what we have so far. We have 2n initial conditions in both cases, but the main difference is we have n second-order differential equations compared to 2n first-order differential equations. So I guess the question is, which would you rather be faced with? Would you rather have a fewer number of second-order differential equations or twice the amount of first-order differential equations? What do you think? Which would you prefer to be faced with? The first-order ones. How come? Probably easier, since it's first order. And we have a few more of them, but still should be easier. From a mathematical point of view, one can think of the transition between the Lagrange and the Hamilton formalism as a variable change. So instead of using Q and its time derivative Q dot, which spans the configuration space, we instead use the canonical variables Q, P, which span the phase space. And the canonical momentum is obtained via the relation down there. And at this point, we can introduce the legendre transformation, because this is precisely the tool we need in order to make this transition. So let's say a few words about the legendre transformation. To illustrate how it works, let's assume that we have a function which depends on x and y. In that case, the differential of f can be written like the following. So I just introduce u and v for the partial derivatives of f with respect to x and y. So this is the this is the starting point. Now, let's say we're interested in making a basis change. We want to exchange the set of variables that we use. And more specifically, let's say we want to change our basis from x and y to a basis u and y, where u has been introduced here. To do so, we introduce a new function which is known as g. And g is the original function minus the product between the two variables that we want to interchange, in this case u and x. So it's the original function minus the two variables that we want to interchange. Because if we do so, we may consider a differential of g. And then inserting df over here, we have achieved precisely the aim we were interested in. We want to change the basis from xy to uy so that an increment in g, the differential of g, is expressed in terms of increments in u and y. So by comparing this with this expression, we can identify these two factors, v and x, in terms of the partial derivatives of g, namely the following. So we've changed the basis from xy to uy, and these two factors are now functions of u and y. The partial derivative of this new function g with respect to u and y. Okay, that's a suitable place for a break.